Okay, let's take a look at this application and practice the t-distribution. It says a medical researcher would like to estimate the average resting heart rate of subjects that are being treated with a new medication. A sample size of n equals 18 gives an average resting rate of 87.2 with a sample standard deviation of 11.31. Find a 90% confidence interval for the true resting rate. Well, same process. We take our sample mean, which is 87.2. We do plus or minus the t-value, right? 1.74, we'll derive that in a minute, times the standard error. And our standard error is going to be the sample standard deviation of 11.31 divided by the square root of the sample size, 18. Okay. How do we know to use the t-table? Because we have the sample standard deviation, not the population standard deviation. Therefore, we must use the t-table to account for that extra uncertainty using the sample standard deviation as a proxy for the population standard deviation. All right, if we multiply these, the t value, by the standard error, we get our margin of error, which is 4.638. So just with this data here, we now know that we're 90% confident that the true population mean is 87.2 plus or minus 4.638. But where did we get this t-value from? Well, we went to the t-tables. And for the t-tables, we read them slightly differently. You have your degrees of freedom in the first column. So since our sample size is 18, we would be looking for 18 minus 1, which would be 17. So this is going to be the row we look at. And then in this table, it's set up based on the tail probability, or you can scroll down and you've got the confidence level. So clearly we have a 90% confidence level, and that means a tail probability of 5%. So you're going to have 5% in each tail. Okay. So if we look at 17 and 5% in each tail, you have 1.74. Let's go back to our data here. So that's where we got the 1.74 for our t value. In our diagram, we can illustrate the distribution in x terms or in t terms. Well, if we use t terms, then we have positive 1.74 delineating the upper confidence level, and then we have negative 1.74 delineating the lower confidence level. And note we have 5% in each tail, giving us a 90% confidence interval. If we want to do x values, then we would need to find the upper confidence level, which would be 87.2 plus 4.638, or approximately 91.8, and it would be for the lower confidence level 87.2 minus 4.638, or approximately 82.6. So we are 90% confident that the true population mean is between 82.6 and 91.8. If we want to interpret it as t-values, we are 90% confident that the true population mean is within negative 1.74 and positive 1.4 standard errors from the mean. Okay, so that's how we would interpret number one. Let's go to two. For this one, it says the average deposit of 20 customers selected at random from the depositors of a local bank is 83.6, with a sample standard deviation of 12.41. What would be a 95% confidence interval for the average deposit of all bank depositors? Same process. What's our average? Well, our sample average is 83.6, so we put that there, plus or minus our t-score times our standard error. To create the standard error, we take the sample standard deviation of 12.41, divide that by the square root of our sample size, which is 20, and we get our standard error. Now, if you multiply that by the t-score, you get a margin of error of 5.808. So we are 95% confident that the true population mean is 83.6 plus or minus 5.808. Where do we get this t-value? Well, same as before, we used our t-table. And we had to use our t-table because we didn't know the population standard deviation. We had to estimate it. right? By using the sample standard deviation as a proxy. In our t-table, we need two pieces of information. One, we need to know what's in the tails, which if we have a 95% confidence interval, we have 2.5% in the tails. And we need to know our degrees of freedom. Well, our sample is 20 customers, so 20 minus 1 is 19. So now let's go to our table. I'm going to go to degrees of freedom of 19 and across to 0.025. 2.093. Okay. Let's go back, see what we get. And that's it, 2.093. Now, in our illustration, we can set our mean at 83.6, that's our sample mean, and our t at a mean of 0. And then we know that our positive upper confidence level for t is 2.093, and our lower confidence level for t is negative 2.093. We can now create the interval for our sample mean. We take 83.6 plus 5.808, and we get 89.41. We take 83.6 minus 5.808, and we get 77.79. So we can say we are 95% confident that the true population mean is between 77.79 and 89.41. We are 95% confident that the true population mean is between negative 2.093 t-score and positive 2.093 t-scores. Either way, same outcome. All right, let's keep going. The next application asks us to identify the appropriate distribution to use. First one says, the average time it took a sample of 45 selected mice to complete a certain maze was 3.2 minutes. The population standard deviation is unknown, but the sample standard deviation is 0.4 minutes. Well, do we use z or t? Well, because we're given the population standard deviation, we are not given, since the population standard deviation is unknown, we can't use z. So we use t, right? And we would use the sample standard deviation as a proxy for the population. But because we're using the sample standard deviation to represent the true population standard deviation, we must use the t-table rather than the z. This one says a sample of 20 sport fishing boats outside of San Diego port showed an average catch of 80 tuna on 3-day trips during the tuna season. The population standard deviation is known to be 12.8. Well, because we know the population standard deviation, we don't have to estimate it with the sample, so we can use z. Okay. Last one, a random sample of 18 families found that they sent an average of 44.7 greeting cards during the holiday season with a sample standard deviation of 8.1. Well, we don't have the population, it's unknown, it gives us the sample. So we need to use the sample standard deviation as a proxy for the population standard deviation, which means we have to use the t-table. Okay, pretty straightforward. The last thing we're going to do in this section is find the population proportion estimate. And for this, we're going to be dealing with a proportion as opposed to other types of data. For example, instead of trying to estimate the population average income or the population average height, we would be looking at the population fraction of something, the proportion of smokers in a population, proportion of people that are over age 50 in a population. Proportions are very common in analyzing social science data. Just like before, we need our standard deviation. If we don't have it for the population, this would be the formula. If we know the standard deviation, then we can estimate it using the sample proportions as a proxy. So we'll be using this formula. From that, we'll create a confidence interval estimate taking our sample proportion plus or minus the z value multiplied by the standard error. Okay, and that's the same as the population or the sample proportion plus or minus a margin of error. From this, you could create a lower confidence level by taking your sample proportion minus the margin of error, or the upper confidence level which would be your sample proportion plus the margin of error. So you see the parallels. We're not doing anything avant-garde here. It's just a different calculation for the standard error and for the standard deviation. Okay, let's practice this. Again, I've done these for us so we can kind of have the answers as we go through them. Let's say we want to estimate the number of accidents that involve alcohol. 80 past accidents were chosen at random. 63 were found to involve alcohol. Find a 90% confidence interval for the true proportion of accidents that involve alcohol. Well, first thing we need to do is find our sample proportion. So if there were 63 that involved alcohol and there were 80 accidents that we looked at, 63 over 80 is 0.7875. That's our sample proportion. So we're going to have 0.7875 p hat plus or minus our z-score, which we'll calculate in a minute, times the standard error. And the standard error is the sample proportion, 0.7875, times 1 minus the sample proportion, which is 0.2125, divided by 80 and rooted. If you do the calculation, you should get 0.0755 as your standard or your margin of error. So we are 90% confident that the true population proportion is 0.7875 plus or minus 0.0755. And the same process as before. We create our normal distribution with z and p. Okay? Z standardizes to 0. P is the proportion mean that we got in our sample, 0.7875, and then we can add 0.0755 to get our upper confidence level, 0.863, and we can subtract 0.0755 and get our lower confidence level, 0.712. So we are 90% confident that the true population proportion is between 0.712 and 0.863. We are 90% confident that our true population proportion is between negative 1.65 and 1.65 z-scores. All right, now how did we get this z-score? Well, we used our z-tables. And if you recall, we need to find the positive, and then it's just negative because it's symmetrical over here. To find the positive, we're looking for 0.95 in our table, right? Because remember, the z-tables start with negative infinity and then go all the way to our upper confidence level. So if you got 5% in the tail, then you must have 0.95 here. So let's go to our z-table and find 0.95. Well, 0.95 would be, we could use either of these. Let's use this one, 0.9505. 1.65 is our z value. And that's what we used in the table, 1.65. Okay, pretty straightforward. Now the last one here, it says a survey asked college students the following question: do you consider yourself a social liberal? The survey questioned 220 students and 168 answered yes to the question. Find a 94% confidence interval for the true proportion of students who consider themselves social liberals. Again, we need to calculate our proportion. So 168 students said they were liberals out of 220. That gives us 0.7636 plus or minus our z-score, 1.88 times our standard error. And we use p hat 0.7636 times 1 minus 0.7636 divided by 220, rooted. That gives us a margin of error of 0.0538. So we are 94% confident that the true population mean is 0.7636 plus or minus this number, 0.0538. We can get our upper confidence level by taking this number and adding this. That gives us 0.8174. Or we can get a lower confidence level by subtracting this number from this. So we are 94% confident that the true population proportion lies between here and here. The z-score is a 94% confidence level. So we need 3% in our tails, which means we're looking for 0.97 in that table. I'll leave that to you. I'm out of time, but I think it should be clear. If you have questions, let me know. Thanks.